Hi, I'm Jomar. Enjoy my videos in my YouTube channel.
Our topic in this video is about mathematical modeling, the heart of applied mathematics. If we are going to consider mathematics as a body of a person, let's have this analogy. The theories in mathematics will be the brain, mathematical modeling is the heart, and the methods and algorithms will be the arms, so that we can reach our goals, and the different application areas will be the legs, so that we can go to many directions. Now, what is mathematical modeling? For me, based on my perspective, mathematical modeling is abstraction. Let me show you a diagram. If we have a real-world problem and we want a solution, because of the complexity of the problem, most probably, the route to solution is impractical, difficult, or impossible. But we can focus on a certain portion of the problem depending on the questions that we want to answer. Then, based on our justified assumptions, we can have a model, and this model is the mathematical representation of that portion of the problem. And from here, we can probably derive a solution. But the route to this solution is not that easy. We need to do analysis, interpretation, sensitivity, evaluation, and validation of our results. To give an example, let's say we have a biological system, in this case, a gene regulatory network. We can probably translate this to mathematical expressions such as using differential equations. And from these differential equations, we can do analysis such as doing numerical simulations. And from these numerical simulations, we can probably draw conclusions that we need to test. Now, what is a good model? A good model is simple, following the law of parsimony or the Occam's razor. It is valid. That is, we can test the results if it follows the real-world system, and we can also test the assumptions that we made. Lastly, our results should be robust, in such a way that if we do sensitivity analysis, our results will not change too much, so that we can have a reliable conclusion. Now let's discuss mathematical modeling process. Here is a simple diagram of the mathematical modeling process. We can start with the observation of the system in consideration and gathering of relevant data. Then we can identify assumptions. Then we can design the model. After that, we can analyze the model, such as using analytic or numerical methods. Then we can interpret the results based on the system that we are working on. After that, we can test if the results are valid. We can also do parameter estimation. And if it is necessary, we can modify the model. This mathematical modeling process is spiral, so that we can improve our model and improve our conclusions. It is important to note that the mathematical modeling process does not focus alone on the design of the model. We also need to observe the system, interpret the results, and validate the results. Mathematical modeling can have different objectives, such as to describe the system, explain different phenomena, predict scenarios, and prescribe solutions to problems. The modeling process follows the scientific method, and it should adhere to the philosophy of science, specifically falsifiability. We can also see that the mathematical modeling process is very similar to the process of the scientific method. What is falsifiability? This is a philosophy proposed by Karl Popper. Simply, this means that our results and theories should be testable. Those theories that are not testable can be seen as pseudoscience. And our results and theories should undergo continuous validation. A theory surviving many tests is considered stronger and stronger in terms of explanatory power. This falsifiability demarcates science and pseudoscience. Let me discuss to you the different types of models. Suppose there is a soccer player kicking a ball, and the problem is for us to predict the trajectory of the ball. One mathematician might do this: to collect data, probably historical data, and fit functions that would fit this data. This type of model is called phenomenological or black box. This is called black box because we don't know the mechanisms why this happens. Our prediction only depends on the data. A second mathematician might do this, to measure the different forces acting on the ball and create a model. This type of modeling is called mechanistic or white or transparent box. This is called transparent box because we know the mechanisms, such as the forces. We can combine phenomenological and mechanistic modeling, and it is called gray box. When we are doing mathematical modeling, we need knowledge about the systems. In addition to that, modeling needs not just critical thinking, but also creativity. Can you model the population growth of bacteria? Can you model the growth of your investment? Did you know that there are certain models that use similar models in modeling growth of bacteria and growth of investments? There are other different perspectives on how we are going to categorize the models, but we are not going to discuss this in detail. To end, I'm going to show you one of my favorite examples of a model. Here, falsifiability or testability is at work. There are physical phenomena that don't work on Newtonian physics. Because of this, there is a shift in the paradigm. Now we have Einstein's relativity. Here is the set of Einstein field equations for general relativity. Einstein created a mathematical model of a physical system. This model is about the force of gravity arising from the curvature of space-time. The theory of relativity of Einstein has undergone many tests. And until today, tests are being conducted, including the gravitational wave detected in 2016 and the first image of a black hole. I hope you learned a lot from this video. Again, applied mathematics, mathematics with a heart. Bye!